connection. Now, coming to the modern wireless evaluation, we know that now we are in the present generation of 5G. So, 5G communication technology plays a very important role with high speed data rate greater than 1 Gbps speed per data. So, we started the era from 1G to 2G, 3G to 4G, 4G to 5G. This is a wireless evaluation era. Now, in 2020, we are using this 5G communication with high speed data rate using the standard communication protocol IEEE 802.11 and some other communication protocols which is to be matched with the wireless systems, and that antenna plays a very important role for transmitting, for uploading and downloading the data. Okay, so my scholar has I have guided my scholar in this area, and we have done 5 objectives, and all the papers are published in essay and Scopus papers. So the main motivation: research on antennas can directly impact. We know that antenna plays a very important role nowadays in communication systems as well as in agriculture field or radar communications, mobile communication, which plays a very important role. Okay, so choosing this research topic, developing an efficient advanced antenna designs, which leads to reduce the sizes and more portable, and it should be embedded on wearable devices and implantable devices. That also plays a very important role in biomedical communication. Implantable devices also plays a very important role in modern day 5G 6G systems. Okay, so our goal is to design a novel antennas that can help to optimize the frequency spectrum usage effectively, and also make the improvement of the wireless communication data speed, high speed data transfer rate in applications of streaming and online gaming and other which we where we had to biotelemetry applications. The patient will be at some other place and the doctor will be at the some other place. In that case, we can transmit the medical data from source to destination. So that's why our motivation is we need to choose these antennas, these Menderline antennas, which occupies less space by bending the lines. Okay, I will show the structure of the antenna, the proposed antenna structure, what we have done in this work. Okay, so in the first objective, to design and implementation of Menderline monopole antenna for S-band applications. Second objective, to design of corner sliced circularly polarized. So we are changing the polarization also by slicing the corners of the square patch, the slices are diagonally. So we get a circularly polarization wave that is done for C-band applications, and to design and implement of a miniature microstrip patch Menderline antenna for X-band application, that is 8 to 12.5 gigahertz. This is a free licensed band, and by a medical application band, frequency Wi-Fi 2.4 gigahertz ISM band, that is also a free licensed band. So we can design the antennas in this free licensed band. So the fourth objective is to design and implementation of double loop antenna for small door locking system using IoT. So in this presentation, we focused on IoT home application, smart home automation, where the door locking system with a small sensing device antenna placed at that place, and we can send and receive the signals by making the by locking the door. Okay, so these are the frequency bands for 5G case, and we know all these basics, and we focused on some of the important bands and worked on the antennas, and we taken the printed materials on a glass substrate, FR4 substrate, and textile material, and we observe the different frequency of operations where they will respond, and what is the gain and what is the VSWR. Okay, and role of antennas, do you know this part also? So coming to the flow chart, how the performance can be done, how we can use or how we can follow the procedure for sorry for making the first selection of an antenna parameter. Return loss plays a very important role for reflection coefficient where the impedance matching should be done, and VSWR is also one of the important parameter. These two are interlinked to each other, and gain of the antenna plays a very important. So selection of antenna parameter, in this case, this parameter, what parameter we are used to select and what we need to optimize. And after selecting the parameter, we need to optimize the miniaturization patch with some loading of material, dielectric materials, or by making some slots, by cutting the patches at the bottom ground plane, defected ground structures, or by using some substracts, metamaterial structures like split ring resonators. We can use we can use those techniques and we can simulate. Okay. So after doing this desired optimization and simulation, we need to observe the selected parameters. Suppose we want to design 2.4 gigahertz. If it is 2.4 gigahertz, then we can develop the antenna. Otherwise, we need to go back and optimize the antenna parameters, length, width, slot length, slot width. All those parameters we need to optimize. So after develop, once it is satisfied, we need to make a prototype antenna, and finally we need to test and verify using vector network analyzer. And this is a process in a we use the software HFSS. We have a licensed software research version in our college. We purchased it within 2017. Using that research version license, we will use HFSS, high frequency structure simulator, for doing the simulation process. And we know all these softwares like CST Micro Studio, HFSS, ADS, all these are the available tools in the market. And coming to our optimization practice. So first, what we have done in the first case, we make an antenna with a straight line. And then we bend that antenna with some bending. See here, we are inserted the bend. The bend may be in the right direction or the bend may be in the left direction. So this is the structure of mended monopole antenna for mobile applications. So this is the HFSS model. Okay. And we have taken half truncated round. And for each length of this monopole and width of the strip, the dimensions here mentioned in terms of FR4 epoxy. Here we have taken the material on FR4 epoxy with a dielectric constant of nearly 1.68, and we simulate this structure in HFS software. And we got the results. These are the results using FR4 epoxy material. It is nearly 2.4 gigahertz, where the patch antenna resonates with a best return loss value and with the best SWR value, standing wave ratio value. And these are the gains obtained in the HFS software. And after that, we fabricate this microstrip line, Mender line, on FR4 epoxy. This is the front view, and this is the back view of the microstrip patch antenna. And with this SMA connector is connected. This is a 50 ohm SMA connector, where the impedance can be matched with this strip line. And after that, we have a vector network analyzer, E5071C. This is the vector network analyzer, E5071C. It used to test any antenna from 300 kilohertz to 14 gigahertz. Above K band up to, we can use this network analyzer. And this is purchased in the year of 2010. And this is a transmission line. At this part, we connect the antenna. And this is the connection point. These are the connectors. Once this antenna connected, here we are getting a curve in this black screen of the VNA vector network analyzer. The dip point observing the value of the VSWR or return loss value on the VE5071C vector network analyzer. See, we are zoomed the results. This is a screenshot of the network analyzer. In our network analyzer, we get only return loss, VSWR, polar plot, and it is a two-port network analyzer. Suppose if you want to test any filter, you can get S11, S12, S21, S22. Like that also we can done, because we are using only antenna. So S11 parameter only we need to consider. So this is the dip point where we are getting a frequency. In simulation we got 2.3. In measured value we got 2.4 gigahertz. Here in the top corner, if you zoom this, in this top corner we will get the frequency dip point and the return loss value. So the resonance frequency 2.4 and 2.5, and another resonant frequency we got at 5.7 and 5.4, two bands, dual band, here one band and here another band, and the corresponding return loss is minus 27 and minus 16 for the same two cases, and this is minus 11 and this is minus 17, and VSWR is 1.09, 1.4, means we need to observe the VSWR value between 1:2, then only that antenna is perfect. And after that, what we have done, we have changed the substract to denim cloth, jeans cloth. Means first case we have taken FR4 epoxy. Second case we are using textile, and these are the results obtained using HFSS. So these are the results. Now, this is the fabrication model. See, this is the denim jean cloth of dark blue color. We have take the substrate. This is the cloth material, and here I am changing the copper to aluminum. We are observe the results for different materials like copper, aluminum. Okay, we know the best conductor is copper, but we have verified for using aluminum foil strip. We have taken aluminum foil strip and we have cut the slice that in the Minderline model, and we paste on a denim jean cloth with an SMA connector with same truncated ground. Same textile antenna is connected to the vector network analyzer. So this is the experimental setup. Bottom two diagrams are the experimental setups for VNA, having a microstrip monopole Minderline antenna with aluminum material. So, and we observe the network analyzer results. Here also we get two dip frequencies. This is the first dip frequency, second dip frequency, and this is the VSWR curve. Please observe the cursor. I am moving the cursor. According to that, please observe. So in simulated, we got 2.6. Okay, measure we got 2.9. See, by changing from copper to aluminum, there is a shift in the frequency points as well as shift in the return loss values also. So this shift in the return loss values means we are not changing the dimensions of the patch antenna, but we are shifting the frequency. This is a frequency reconfiguration. So we are changing from one frequency point to another frequency point, and the VSWR value for all these cases we are getting 1:2, means 1.1, 1.6, and 1.3, 1.1. So these are the results we got VSWR value. Then what we have done, we have go for the we have changed the design from a Minderline to a inverted T shape with a cap model. See, this is a small miniature patch antenna, low profile band, and we got some band notches. Means what frequency we need to remove. Means remove means notching means nothing but at that frequency the strip antenna should not be operated, and other frequencies the strip antenna should be operated. And DRA antennas, dielectric resonator materials, are also placed on the top of the strip for various applications. But here in this slide, we have taken only the inverted T shape and with the two slots at the ground plane. In truncated ground plane, we have taken two C slots. We can call a C slot, but extended C slot. And this is the proposed model with dimensions of this structure. We have taken one base paper. In that base paper, we have taken these dimensions. The modification of the base paper, we have put some defected ground. Defected ground structure means we have cut the slots on the ground plane, and we got this result. See, this band is notch band where the this entire band is not responding, and this entire band is again responding. Means we are getting one frequency, sharp frequency, and another some wideband response. And these are the gain plots and VSWR plots. And we fabricate this small inverted T monopole antenna, and we connect it to the network analyzer, and we have observed the return loss curves on the vector network analyzer as well as VSWR value. But in practical case, there is a small change. We have not get the wideband for the second dip frequency value. So compare if you finally we can observe the results from this notch band monopole antenna. Frequency of operation we are getting, these are the different frequencies of operation, different return loss values, and VSWR if you observe 1.2 and 1.06, so it is between 1:2, and gain is also below above 3 dB, so we can consider this for particular band applications where we can respond the entire band. The antenna can be operated with low VSWR value. And after that, we have taken a third design, square patch. Square means four sides are same, but diagonally, you need to opposite two directions. Diagonally, slicing has been made. See, in this structure, L3 is sliced. Sliced means cutting. So we sliced the diagonals, and we inserted a U slot inside the square. So this is a proposed model already exists in the literature. But what we have done means in perfect square U slot, we have sliced the left top and corner with the left and right direction. So design of corner slice circularly polarized patch antenna is proposed using FR4 epoxy subtract. And these are the simulation and practical results we observe. And finally, this main slicing and doing cornerly, what we got means we got circularly polarized. The previous antennas, design 1 and design 2, are linearly polarized. By slicing the corners of this square patch, we got circularly polarized. And this circular polarization, we observed axial ratio curve 0 to 3 dB point. See, this is the proposed model fabricated antenna, and this is a proof-fed antenna. In the previous case, they are the edge-fed antennas. This is for the proof-fed. Bottom we given a probe SNA connector for feeding the antenna. And this corner sliced patch antenna connected to the transmission line of the network analyzer, and we observe a dip point, maximum dip point here in the network analyzer. So the resonant frequency simulated is 3.5 and measured is 3.2 gigahertz, and these are the return loss and VSWR gain values of the simulated and measured of the proposed antenna. So this is like this. We consider different structures. All the structures are operated in a particular band of frequencies, fabricated and tested using vector network analyzer. And the fourth design is a design of a miniature microstrip Minderline antenna for 5G application. This is our novelty new antenna where we are used this in Minderlining in the small patch, and the dimensions of the patch is very small. It is a 1 centimeter. Total the antenna size is 1 centimeter, and we can easily connect this 1 centimeter antenna to this IoT kits. We have experimentally verified and connected to the IoT kits also. Okay, the single element of the microstrip with Minderline line is designed and fabricated for X-band applications, and we observe the axial ratio, and we observe the VSWR value, and we observe the gain and return loss of this curve. And these are the proposed dimensions of the antenna in internal structure and external structures. And these are the results we got. See, the size of the antenna is nearly one subtract size is 1.5, but antenna size, what is the copper material that is etched, it is nearly 1 centimeter. So very small antenna, and we have take the photographs, and background we have a truncated ground, not full ground. And this antenna is also connected to network analyzers, very small antenna. See the size. And these are the dip frequency points. We got two dip frequencies. One is this is the first dip frequency, and this is the second dip frequency. For the second dip frequency, we got a good return loss value and VSWR value, and we observed the radiation patterns for both cases, VSWR value, and we tested this antenna in an anechoic chamber. We have not we do, in our college we don't have anechoic chamber. With the help of RCI people, we take a permission, and this is a chamber enclosed with observers. These are the blue color pyramid materials are the observers, and this is a circular disc. In this we connect the antenna, and this antenna will be placed in copole, means vertical pole and horizontal pole, and both case we will put a transmitter at the in front of the antenna at a distance of 2d square by lambda, and we can observe the simulated and measured results both case, and for different resonant frequencies. So the fabricated antenna we simulated for 8 to 12, in that 11 gigahertz we have taken, and a measured value we got 10.63, return loss minus 21.2, and observed measured minus 23 dB. VSWR is 1.13 and 1.2, and gain like that. Everything we observed, and we published this work in one of the Scopus journal, so that which is a somewhat it is also good journal. I will show the list of our publications also. So like this we observed, and after that what we have done, we have taken the antenna. This is a transmission of message of a fabricated antenna which is connected to GSM module. This is a GSM module. We have so many modules in IoT based kits. Okay, in that this GSM module we connected the antenna, and through these connectors we use a system, and we transmit a message. Testing of fabricated design antenna in real-time mobile applications through IoT SIM 900 module. So we have this software, and this module is connected to this laptop, and antenna is connected to this antenna part, and we transmit the signal at a sending one text message, and the text message is observed in the monitor. See, this is the testing and fabrication in real-time mobile application through IoT. So this is the entire IoT kit, and we connected this antenna. We fabricated this antenna in our lab in our college only, but the testing through network analyzer we have done in our college only. But radiation patterns observed in the anechoic chamber, that test antenna is connected to the connector of this SIM 900A module. This is one of the module used for real-time mobile applications where we can transmit the information from the host point to the destination point with a perfectly connecting line. So the frequency bands can also be set by AT commands. Through AT commands, the frequency bands is set to 10 gigahertz to 12.5 gigahertz, and this antenna is operating between these two module bands. So signals can be transmitted, text messages can be transmitted and received to mobile to the laptop. See the results. See, testing and fabrication of design antenna in real-time mobile communication. We transmitted one information, sending high message here, and at the receiving case, we got the message for both cases through mobile. See, our my student KSN, he in his mobile number, we transmitted one message, and these two messages from sim 1 to sim 2, two sims, we observe the results in the monitor. So after designing and testing, we observe finally conclude that these antennas can be easily embedded and easily printed on IoT boards, and we can successfully transmit and successfully receive the messages from the mobile phones from one band to another band. And after that, what we have done, smart home automation. We our main goal is smart home automation, doors with glass substrate. See, in most of the houses, some doors will be there. When a person enters, sensor will be there. The door will be open. When the person move far away, the door will be closed. Some sensing material will be there, object sensing material. We have taken the same glass, but instead of sensor, we have kept one double loop antenna fabricated on the glass substrate, which is operated in S band, X band applications. So to make the door automatically open and automatically close based on the transmission of the signals. Okay, so double loop antenna, we have taken some loop material, out loop and inner loop. These two loops are oppositely excited and made with a relative permittivity of 5.5. And first we observed this in simulation of HFSS software. So this is a taken a radiation box, and this is a double loop. See the HFS model, and feed point here we connect, and this is a loop antenna, rectangular loop antenna, and the outer loop is connected to the inner loop with some electrical contacts here, up and down. We have two contacts. So inner loop and outer loop. These two loops have different lengths of electrical variations. So, and these two loops are, we can use copper and we can use aluminum foil, and we cut that material and paste that material on the top of the substrate. And these are the different results we observed using HFSS. These gain plots. See, this is a fabricated antenna. See this diagram. This is a glass substrate. Why we taken glass substrate means in our proposal project work we have used glass as a door. Means we can more mainly so many doors will be there with a glass material, automatic on and off. So the SMA connector is connected to the outer loop with aluminum foil, and inner loop is there which is connected to this small connecting patches. So this fabricated antenna is integrated with the design and development of IoT systems for smart door locking as a prototype. And we connect this antenna to the network analyzer, and we observe these different resonant frequencies, multi bands, and which band we got good return loss, good VSWR. At that frequency, the door can be make on and off, means close and open. And this is a prototype model made by our student. This is a some small house, and we kept a door, and at the door we locking system. This double loop antenna is connected to this point with a some battery voltage supply of the system. And in the design of the development of IoT system for smart door locking, ESP32 cam. A module is kept here, which is responsible for taking and sending uh, pictures of the persons standing near the door. That also we incorporated in this one. By blinking by this app, blinking app to control the entire operations of the system through internet. So next slide I will show the how the loop antenna responds and opens this mole. See here, this ESM ESP32 module we have uh, used on the breadboard, and that is connected to this door locking system. Here the door locking system will be there, and some glass antenna, double loop antenna, here it is placed. So some sending of the signal and excitation of this antenna, this locking can be done with automatic open and close. See, so the case one, cam tracking as a picture. Case two, door open through unlock command. So these are the steps, different steps. When a person press the bell, the notification will appear on the screen. Step two, when we open the notification and rewrites some blinking app, take picture, it automatically take the picture of the unknown person or known person, which is who is stand before the door. After taking the picture is sent to the admin, and the person knows to a particular owner of that house. He unlocks the door by clicking unlock. Once the command unlock is clicked, the double loop antenna will be excited, and the double loop antenna which is located here at the back side of the door, it is will be excited. Based on the excitation of the antenna, the signal will be enabled, and this door locking will be open. So like this, the door will be open. Lock and unlock can be done with some commands. Okay. So in this case, we have done mainly for glass substrates, and we can take other materials also FR4. But if you take an FR4, the door will be a glass, and extra this FR4 clad will be placed on that, and it will increase the total system cost and weight also. Okay, so to overcome that problem, we have taken the glass material and we put that sticker, a copper sticker or aluminum sticker. You can take anyone. In this case, we have taken copper. We can use aluminum also for better improvement of the results. Okay, in this work, mainly focused on miniature Mendelin antenna for modern wireless applications, for as well as IoT applications like home automation, and we can extend the work to biomedical application. We can extend the work to like agriculture applications. We can use any case, and circularly polarized antenna also we observed, and different materials like FR4 epoxy, glass substrate, denim jeans, like that we observe the different materials and fabricated the antenna for IoT applications. And the future scope of the work can be extended to wireless body area network, which is mainly for biomedical on body and off body conditions we can use and we can observe. And the proposed antennas can also be extended for upcoming 6G applications. Now we are in the age of 5G, and the work can be extended to 6G also. Okay, and in future this work can also be done by using some AI based applications linking to cognitive radio, where the bands cognitive radio which plays a very important role, the utilization of unused spectrums. We have so many spectrum bands, spectrum holes are there in the spectrum, that unused bands can be artificially identified, which spectrum is vacant and which spectrum is full. That vacant spectrum can be used by the antenna by using the frequency reconfigurable technique antenna. In the previous presentation, our sir presented on reconfigurable antennas, that also we can use here for cognitive radio applications. And after that, what we have done, we have optimized some. We shifted our work to the meta surface antenna designs. I will show you some of the designs. Please wait. We have presented this work in VAM's presentation, IEEE conference. So design of circularly microstrip antenna with meta surface superstrate for IoT applications. Okay. So meta surface superstrate. So we have taken the meta surface material, that is nothing but meta material, and we place this material on the top of the patch antenna, at a distance of lambda g by 2. So coming to the discussion. Uh, so these are the unit cells. We know the about metasurface unit cells. We can take any shape: Jerusalem cross, circle, helix, loop, square, anything we can take. Metasurfaces which are placed with some making the movement of the direction of the wave in the opposite direction, so that these are naturally not available, but these are the artificial magnetic materials, but we need to make the relative permittivity and epsilon value, mu and epsilon value, both will be in negative way, so that these materials are mainly used as reflectors, observers, and they can use it as a lens also.
Excuse me, sir.
Hello?
Sir, one of the participant asking, can you give any radar application, sir?
Radar.
Radar application, sir.
Now we can also use these metasurface materials for observing materials, where any radar signal is transmitted. That signal will not be reflected to the back to the radar side. That metasurface will observe that echo pulse. If that echo will be observed, that reflected signal will not be sent towards the radar transmitter. Like in military applications, where the moving target is there, if the radar is detecting the target, transmitting a signal and getting the reflected echo. But if that target, like aircraft, is made up of with this reflecting surface, metasurfaces, there we can use it as like a stealth. Stealth means target is there, target is moving in front of the radar, but the target will not be detected. That can be done using this metasurface materials. But in my work here, I have used this metasurface super material as a superstate, which is placed above the substrate and acts like a lens. I will show you the antenna. See, first I have taken a small square patch antenna. This is circular patch antenna. This is a some like a rectangle, triangle, circle. I have taken a circular patch antenna at the base substrate. Above this circular patch, we placed a superstrate. And for a single circular patch, we observe the simulation results at 13 dB, return loss minus 13 dB, and VSWR 1.5, and gain like this. And what after that we have taken plus symbols. Jerusalem cross is already exist in the literature. We modified Jerusalem cross to ordinary cross, like a plus symbol of array 3 by 3 metasurface cells with same metamaterial properties, which is placed top of the patch. Bottom we have a circular patch, and top we have a metasurface unit cell 3 by 3 unit cells. Okay, so by placing this cell, the radiation from the circular patch antenna touches the top superstate, and it acts like a lens. Means we know about the concept of lens, focusing the radiation into a particular direction, so that the gain can be improved. See, this is the fabricated antenna, and we at the bottom we have kept the circular patch antenna. At the top we have kept this metasurface. This is a metasurface unit cells, 3 by 3 unit cells with plus shape, and there is a gap between these two patch, and SMA connector is connected. Whenever the patch excited the circular patch, the signals radiated from the circular patch will touch the metasurface unit cell. So the broad beam means the apple shape of the radiation pattern beam will become a narrow beam. So particular direction, the directivity can be improved, the gain can be improved. So like this superstate plays a very important role, and this is the tested network analyzer of the superstate. We use thermocouples at four sites at a height of lambda g by 2. Lambda g is the operating wavelength of our resonant frequency. We know the patch antenna. For that, we will calculate the guide wavelength, and that guide wavelength by 2 at lambda g by 2, we have kept the distance. And we can also observe the changing the lens position less than lambda g by 2, exactly equal to lambda g by 2, greater than lambda g by 2 for all the cases, and we observe the graph. The results of the proposed metasurface antennas, the results of the proposed both for simulation and practical, we observed here, and we plotted the graph here, and VSWR graph, and gain versus frequency also we observed. And see here, measured gain, proposed metasurface antenna, and simulated gain of the proposed metasurface antenna. We got 6 dB for simulation, measured for 5 dB. In ordinary case, without metasurface, 3 dB, and it will be shifted to 6 dB. And these are the comparison of the metasurfaces measured and simulated results of the proposed antenna. Please stay. I will show you some of the graphs. Please stay in line. Okay, comparison of these results. If you see this, both practical and simulation antennas, we observe the measured value and simulated value for gain, return loss, and VSWR. Okay, and another structure I will show you. And nowadays, so many people are using some optimization technique. In the proposed work, we observe the high gain meta surface antenna using hybrid atomic orbital search and human metal search algorithms. In olden days we can use PSO genetic algorithm like that, but nowadays blue whale algorithm, atomic search algorithm, so many advanced algorithms are there to optimize the patch antenna to get the good results. Okay, and the code is developed in MATLAB, and we observe the graphs in the MATLAB of different cases, and the proposed antenna is fabricated and tested. So this is the proposed model. So meta surface antenna design, to calculate the antenna parameters, and the parameters we observe the bandwidth, return loss, directivity and gain, and the proposed optimization here used is hybrid atomic orbital search and human metal search algorithm, and check the antenna efficiency, calculate the antenna parameters. This is the proposed methodology, and this is the meta surface design. And meta surfaces are the artificial materials having the properties which is not found in any natural material. Okay, so for that structure we linked the high gain meta surface optimization technique, and we observe the length and width of the patch using this optimization technique, 14.7 mm and 3 mm width. And for this cell we observe the return loss VSWR, and after that we observe some of the graphs. See, this is the plus shape metamaterial unit cell. We observed first in simulation model, and this unit cell is implemented to circular patch, what I have shown in the previous presentation. Okay, so like that we can use the optimization algorithms, advanced optimization algorithms, and we can observe the structures of the patch, this metamaterials structures, meta surface antenna structures, and we can use this as a superstrates. So parameters optimization using hybrid method of approaching this algorithm. It is the hybrid form of the atomic orbit search and human mental search algorithm, where we can use the better performance, we can get the better results of the optimization technique. And this code is developed on the MATLAB, or we can also use Python. Hello. Hello.
Hello, చెప్పండి సార్.
My voice is audible? Please stay.
Audible సార్.
Okay.
Sir, hello. Sir. Hello, sir. Sir. Hello, sir. వినిపిస్తుంది సార్. ప్లీజ్ రిమూవ్ దట్ పార్టిసిపెంట్ సార్.
సార్ యాక్చువల్లీ
సార్ ఒక 5 నిమిషాలు సార్. సార్ హలో సార్, వాయిస్ వినిపిస్తుందా సార్?
yes sir, voice is audible sir.
ఓకే ఓకే, నాకు మధ్యలో డిస్టర్బెన్స్ వస్తుంది.
yes sir, yes sir, yes sir.
Please. Here optimization results of the proposed optimized results of the proposed and results of the proposed metasurface antenna.
Sir, please remove that participant, sir.
సార్ మాట
Suresh, sir.
తెలుసు సార్ తెలుసు మాట
Sir.
యాక్చువల్లీ డిస్టర్బెన్స్ సార్ వైపు నుంచి వస్తున్నది
ఎక్కడ నా దగ్గర ఏం లేదు సార్.
అవునా సార్, చూస్తాను సార్.
ఒకసారి చూడండి.
సార్ ఇప్పుడు ఓకే సార్. సార్
Sir, you can proceed, sir.
ఓకే సార్.
Satyanarayana, sir.
నో ప్రాబ్లం.
Okay, sir. Okay, carry on, sir.
Sir, ikkada graph. If you observe the graph, comparison of directivity and comparison of gain with respect to the optimization of the proposed patch antenna. Optimization results was proposed in this metasurface antenna. See here, directivity versus frequency. Directivity was frequency. Here we observe this model, and the same results can be obtained and observed for the microstrip patch antenna. And these are the different comparison of efficiency and comparison of return loss. So methods using this methods used is in MSA genetic algorithm, and MSA using this MSA hybrid optimization technique. These are the results we got. Different frequency bands 6, 10, 14, 18, and frequency bands 6, 10, 14, and 18. And these bands are proposed for different cases, and we obtain the measured values and simulation values for the different cases. See here, and radiation efficiency and return loss. Radiation efficiency and return loss for this case. Radiation efficiency. Radiation efficiency and return loss. The methods. సార్ నా వాయిస్ వినిపిస్తుందా?
సార్ మీ వాయిస్ వినిపిస్తుందా సార్?
డిస్టర్బెన్స్ ఎక్కడి నుంచి వస్తుంది? So we have taken a rectangular patch antenna. At the top we have taken a 3x3 cell, unit cell, and we make that antenna fabricated and tested. For that case we observe the results. Hello sir. సార్ నా వాయిస్ కట్ అవుతున్నట్టుంది.
సార్ వినిపిస్తున్నా సార్, వినిపిస్తున్నా సార్.
ఒక నిమిషం ఉందండి సార్.
ఎవ్రీథింగ్ ఇస్ క్లియర్ సార్.
1 minute please stay.
Sir, Satyanarayana, sir.
ఇప్పుడు వినిపిస్తుందా సార్?
Sir, వినిపిస్తుంది సార్.
So these cells are proposed using metasurface antenna design, and first initially we have taken a rectangular patch with a unit cell, and above the patch we have taken a 3x3 array cell, and in the first case we have used a circular patch, but in the second case we have used a rectangular patch, and both will be simulated and tested using the simulation point of the graph. These are the simulation and results.
Sir, 1 minute, sir. 1 minute, sir. Some of the participants asking a few questions, sir. Question number 1 is which optimization is good for latest antenna research field, sir?
Now we have so many optimization techniques, and blue whale algorithm is there, and atomic search hybrid optimization techniques are there. These techniques are used. These techniques are used for the simulation of the results.
Sir, another question is, while designing meta surface unit cell, what analysis we should take into the consideration for efficient performance realization, sir? For efficient performance realization.
Efficient performance means first the cell unit cell should be designed properly. The cell dimensions plays a very important role, and the adjacent cell we need to observe the coupling effect, mutual coupling effect. So the size of the cell plays a very important role in the present and all cases. So you have to observe clearly and carefully.
Sir, I like to rectify my question. The question was like, suppose I have designed something and I am getting some graph. Now, how to extract the information that my graph is correct or my graph is appropriate?
So, whatever the optimization technique you have used, based on the optimization, based on that you have to use the response. See, for example, there are so many combinations and permutations are there. There are so many permutations. Hello, sir, my voice is audible?
Yes, sir. Please continue, sir.
See,
yes, sir, audible, sir.
Which optimization you have used, that plays a very important role, and the optimization which has a more response like gain. What are the parameters you have constrained into the picture? Dimensions of the patch, dimensions of the cell, and after that calculating the dimension of the cell, we need to observe the radiation properties in putting in a unit cell into a that is called one theory is there in metasurface case. You have to observe the cell in all the combinations, and we need to take the results. So the optimizations are so many optimizations are there, and in the proposal in this case we have taken this hybrid advanced model human search optimization technique, and beyond this also there are so many methods are there. You can get the good results. See here we have taken this graph, and we have observed the cases of the different algorithms with genetic algorithm and human search algorithm, atomic search algorithm. For each cases we are using the frequency for different bands, and in the what is the best case we got, for that case we fabricated the antennas and simulated, and these are the proposed antennas, and we make only for circular patch antenna, which is shown in this PPT. See here. This. See, in VAM's presentation, we proposed that this is the patch we have done, made using the vector proposed algorithm. Any doubts? Any doubts?
No, sir. Clear, sir. Thank you, sir.
Please wait. Please wait. If you have any doubts, please ask.
Sir? Hello, sir.
Madam, please wait, madam. You will be available within few seconds.
Satyanarayana, sir.
Sir, please tell.
Sir.
ఇంకా నా డౌట్స్ ఉంటే అడగమనండి సార్.
Okay.
లేదంటే నా సెషన్ క్లోజ్ చేస్తాను.
Okay, sir. Wait a minute, sir. One of faculty asking. Please, ma'am, ask, ma'am.
Sir. Sir, in antenna beam forming, sir, while doing HFSS, can we can direct the main beam in desired direction, while can we put nulls in the undesired direction, sir?
Yes, we can also put nulls in the undesired direction.
How, sir?
Because where the field we can look at the design in such a way that we can observe the cases of different radiation patterns where the main lobe beam should be angle and where the null should get to, suppose for example both side direction we need to get null, or in other direction we need to get, that should be observed by using the different cases.
Okay,
And
sir.
beam steering can also be done by using some uh, switching techniques, beam steering switching techniques. That is a different scenario, different concept, and this is a different concept, madam.
Okay, sir. Sir, can you share your mail ID, sir, so that we can contact if we
Okay,
have
okay.
any doubt.
PROF MSN 26. PROF MSN 26. PROF MSN 26 @gmail.com. Okay.
PROF MSN.
PROF MSN 26 @gmail.com.
Okay, sir. Okay, sir. Thank you, sir.
Okay, thank you. Okay. Thank you, Tilak sir.
Thank you, sir. Thank you so much, sir. You are given valuable information to all the participants, sir. Whoever doing their research in antenna field. Thank you so much, sir. Satyanarayana, sir. Sir.
Thank you to all the participants. Thank you.
Thank you.
Thank you, sir. Thank you, sir. Bye, sir. Good night, sir.
Good
Good
night.
night, sir. Thank you, sir.